There, welcome to the introduction to forces. I'm Mr. Sand, and today we're going to define force. So, what is a force? Well, a force is anything that accelerates something else. So, it's a push or a pull on anything. So, if you push on your desk, or if you pull on, I don't know, a pen or a piece of paper or anything like that, anything is a push or a pull, that is a force on whatever object you're pushing or pulling. Um, to jump into the first law of motion here for Newton, it has written down here, this is straight from the Principia. It's that every body preserves in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by forces impressed. So, what the hell does that mean? It means, well, think about it. What does it mean? It means that if something is in motion, it'll stay in motion unless acted upon by an outside force. Or put more rigorously, something is in motion. So let's say this little box right here is in motion. It's going. It'll stay in motion along a straight. Oh, that should be straight. A straight line. This is a horribly drawn straight line. A straight line unless acted upon by an outside force. So it'll continue to move unless there is a force that acts upon it. The force could bump it this way, the force could pull it this way, the force could go against its motion. It can do whatever you want. It's a push or a pull or whatever, anything that changes its motion. That is a force, actually. That is even a better definition than a push or a pull. It's anything that changes a motion of something. That is a force. So, that's Newton's first law. Something stays in motion along a straight line unless acted upon by an outside force. But of course, it's not going to be that easy for us. We have to draw little diagrams to show how forces behave. So let's just say, I don't know. Let's look at a problem here. Let's say I'm looking at warm-up problem number 5. Let's just go through all the warm-up problems right now. Warm-up problem number 1, it says true or false, an object let's do an object on Earth at rest has no forces acting upon it. Is that true? So something on Earth, just at rest, let's just say, I don't know, a pen that's resting on your desk. Is there any force that's acting upon that pen? Well, there is, actually. If you've got a pen or a pencil, pencils are easier to draw. So I will sort of draw a pencil. There we go. That's a pencil. It's at rest on a table. There's a table. It's at rest. It's not moving. But there are forces involved here. There's a force that the pencil or pen is being accelerated towards the earth. If that table were not there, it would be going downward. So there is a force due to gravity on that pencil. There's also another force, the force of the table that's pushing up against the pencil. So that force we'll call the normal force, or Fn. If I use an uppercase? Yeah, I use an uppercase N. It's a normal force. So these are contact forces here. Or this is a contact force, I should say. This is a field force. So a contact force is something where an object has to be in contact with the force. So here the table and the pencil are in contact, so that force is a contact force. Here the pencil and the earth are not in contact. This force right here is due to the earth. If I draw an earth over here, there's the earth. The earth is right here, saying hello. Earth. So the earth is pulling it towards itself, and actually you'll find out soon that the pencil is pulling the earth towards it, but this force is much greater, so we'll just consider this one. The force here is a field force, and that's the only field force that we'll consider in this class. There's also magnetism, but we won't consider that in this class, just gravity. So this is a field force. It's a force because it's a force that's experienced by an object in the field of another object, and the field here is gravity. So here we go. We've got these two forces, a contact force, a field force. We're doing pretty good. Some other forces to consider. There's a spring force. So if you coil a spring, the force that spring, let's see, a force that spring will exert on an object, that's a spring force. It could also be pulling back if it's a spring force too. Tension is the force. We're going to consider that every kind of rope or every kind of wire is something that does not extend. Because if it extends, then it's a little bit more tricky to think about. But let's just imagine that we have like a light bulb that's hanging. Here's a light bulb. And it's hanging on a string, and the string's attached to the ceiling. Well, from the light bulb's perspective, there is a force going on here. Well, the force, it's being pulled towards the ground due to gravity, but there's also a force right here. This force in this string is a tension force, so there's a tension force pulling up. Now, if these forces are the same, they will cancel each other out. They are vectors. They will cancel each other out. So if this tension force is as much as this gravity, then there will be no movement by this object. The forces will cancel each other out. So the only time you ever get motion is when there is a force that is greater than another force. Oh, I should not say that. Let me back up a second. So if you have something in motion and you want to change its motion at all, so I'll stop drawing those arrows like that. If you have an object that's going in motion, just follow the cursor right here. The cursor is in motion, okay? To stop that thing in motion, you have to apply a force to it. If that thing is in motion, it could have forces on it. It's just they're canceled out. But in order for it to stop or to change its motion at all, there needs to be an outside force acting upon it. Likewise, if there is an object just at rest, like this pencil right here, there are two forces right here you can see. They are acting on that pencil. But they cancel out. Their net force is 0. Sometimes what we describe as a net force is we say the sum of all the forces, that little sum sign, the summation, that Riemann sum sign, means sum of all the forces, or the net force acting on an object. Here, it's 0. Here, in this light bulb scenario, the sum of all the forces is 0. All right. I think we've covered most of the notes. Let's go on to the warm-up problem number 2. True or false, an object in constant velocity along a frictionless path has no net forces acting upon it. That's true. No net forces. I'm sorry. No net forces acting upon it. Right, that's what we just went through. 3. True or false, a force causes a change in position. Well, doesn't have to, because a force right here, there's a force that doesn't cause a change in position, because these forces will cancel out. So it's not necessarily true, so that 3 is false. 4, true or false, a force causes a change in velocity. Let's see here. Does it cause a change in velocity? Well, yes, doesn't it? Not necessarily. Aha! You can have a forces right here, that's a force right here, it doesn't change its velocity, but let's say that you have an object and you just push it, well then it's changing its velocity there. Yes, a force could cause a change in velocity, but not necessarily. It's kind of tricky. 5, draw a free body diagram of someone holding a baseball. I think you can do that, but I'm going to draw, here we go, I'm going to draw a nice little stick person. I'm going to use a different color here. I'm going to use salmon. Here's salmon. Here's a stick person. There they are. They're holding a baseball. There's a little baseball. Now I'm going to use a different color to show the forces. There's a force. What forces are acting upon this? You should be able to guess this right now. You should say, well, Mr. Sand, obviously, there are two forces. There's a force due to gravity pulling the baseball down, but there's another force. Why doesn't it go down? It's staying in the same spot. Well, the reason it doesn't go down is because you've got a force that I'm just going to call F, hand, that's pushing back up equally and oppositely. Here they should be equal and opposite. The arrows are obviously pointing to a different direction here. They should be straighter up and straighter down, but they cancel each other out. It's a very small picture. I should have drawn bigger, but oh well, you get the idea. For the rest of these problems, you're going to be drawing other free body diagrams. Here's a tip for free body diagrams. The free body diagrams just show an object. You normally will pick the middle of an object. Let's say you've got a box. Here's a box. And let's say that box is suspended by, let's say it's suspended by a rope right here, and that's attached to the ceiling. Okay. For free body diagrams, all you care about are the forces acting upon an object. You're not caring about the motion. So in this case, there is no motion. The box is just stationary. Let me erase this to make it clear that I'm just talking about this box. So the box is just stationary. So what are the forces acting here? You just draw the forces with the arrows. You're not drawing the motion with the arrows. That's different. You just draw the forces. So here, you draw from the middle of the object. There's a force due to gravity. There's always force due to gravity whenever you're talking about an object on Earth. And then I like to use different colors for the different forces just to make sure it's clear that they are different. Here's grape. Then you also have a force here that should be equal and opposite if they are indeed canceling each other out, and they're not, and this box isn't moving. So these two are canceling each other out. Now, you could have another force. Let's say that you have a person over here who's pushing this box. You have a stick person over here who's pushing this box. It's a really big box. And he's like, "Arr." There he is. He's pushing. Arr. He's pushing this box. So the force is going in this direction on the object. So we could say that the force would be like this. This is the force due to the person. You always write the subscript right here of what the force is due to. So the force on the box due to the person is going that way. So here, these two forces will cancel out, this force and that force, the tension force and the gravitational force. But this force does not get canceled out by anything. If there was a wall here, then yes, it could cancel that out. But there is no wall there. The force is going to be pushed in this direction. And the box, will it move? Yes, it'll move because you've got a force that's not balanced in any other direction. So it's going to move in that direction right there. Okay? That should help you. Let me know if you have any questions. Goodbye for now.